In the previous lecture, that is in part 1, we have discussed luminescence, why it occurs and what are the different examples in real life where we see luminescence. Later, we discussed electromagnetic radiation, its characteristics, what is electromagnetic spectrum, and then spectroscopy. In spectroscopy, we looked at two types of spectrum, line spectrum and continuous spectrum. Continuous spectrum is where the electromagnetic radiation contains all the wavelengths, while in line spectrum the incident light only contains specific wavelengths corresponding to specific electronic transitions that has occurred in the atom which has emitted it. We have used Bohr's model to explain the different electronic transitions corresponding to different spectra by taking hydrogen as an example. However, this model is not sufficient to explain the complex interactions and transitions that occur in the atoms with higher number of electrons as well as complex molecules. In today's lecture, we'll be briefly going through molecular spectroscopy, and later we'll discuss the applications of spectroscopy. Further, we'll discuss specific concepts of where this spectroscopy is used in scientific research, and finally we'll discuss about chemiluminescence, which is one of the experimental techniques that is based on emission spectroscopy. Now we'll discuss about the molecular spectroscopy. Previously, we have discussed about the emission spectroscopy of atoms, specifically for hydrogen atom, and we have mentioned that the Bohr's model can be used to estimate the different electronic transitions corresponding to different spectral lines in the emission spectrum. But this is accurate only for hydrogen atom, and the model becomes too simple to explain atoms with higher number of electrons. And in molecules, the energy states are not only limited to the electronic states and the energy levels, but other energy such as rotational energy and vibrational energy also exist, which makes molecular spectroscopy complex. So, this complexity leads to a large number of closely spaced lines, sometimes appearing even as bands rather than individual lines in the emission spectrum that is obtained from the molecules. Similar to atoms, when the excited molecule returns to lower energy state, it releases excess energy in the form of electromagnetic radiation. However, the emitted light can have different wavelengths depending on specific transitions, which are not only electronic transitions but also vibrational transitions and rotational transitions. Here in the schematic, it can be seen that the dark lines corresponding to n equal to 1, n equal to 2, and so on are the electronic energy levels, whereas the light blue lines are the different vibrational energy levels present within those electronic energy levels. And there are further more closely spaced rotational energy levels within these, which are denoted by green lines. So the transitions in molecules may occur between different electronic energy levels, or between different rotational energy levels within a electronic energy level, or between different vibrational energies within electronic energy level, or even the combination of rotational energy level to vibrational energy level within or between different electronic energy levels, and so on. The electronic transitions result in the emission of visible light, ultraviolet light, and infrared light because the energy gap is high compared to vibrational and rotational transitions. The rotational transitions have the longest wavelength corresponding to lowest energy because they are closely spaced. The molecular spectra can be very complex due to these factors, And other factors that can affect it are collisions and isotope effects. In the previous slide, we have seen why molecular spectroscopy results in complex line spectrum where the lines are so closely spaced they can even appear as bands. This is because of the presence of different rotational vibrational energy levels in addition to electronic energy levels which are closely spaced with each other. Here on the right side, emission spectra for different elements and molecules have been provided, and we can see that from top to bottom as we increase the complexity of the system, where helium being the simplest system with single atom and two electrons, to xenon with large number of electrons, and water vapor with three molecules. We can see that in case of helium, the spectrum looks like a line spectrum with individual lines, discrete individual lines at specific wavelengths. However, there are closely spaced lines which appear as bands even in helium. When we go to hydrogen, the system is more complex because even though it has the same number of electrons, that is 2, as helium, here hydrogen molecule contains two atoms with a pair of energy levels of the two atoms of their own, and because of which large number of electronic transitions occur in hydrogen molecule, resulting in lines in the spectrum which are so closely spaced that they appear as bands. Similar is the case for other complex systems as well, as you can see. Now coming to the applications of molecular spectroscopy. Molecular spectroscopy, because of these emissions and these spectra, it provides insights into the structure, properties and behavior of molecules. Because as we have already discussed, both rotational and vibrational modes will also contribute to the emissions of the spectrum. So the emissions will also give insights into the vibrational and rotational modes, which indirectly give us information about the orientation and shape of the molecule and arrangement of the atoms in the molecule. Some of the applications for molecular spectroscopy include identification and analysis of unknown compounds and determining their structure. Quantitative analysis is another application where if we have a solution or a mixture with a specific concentration of a given molecule, then molecular spectroscopy can be used to measure the concentration of a specific molecule in a sample. Another example is chemical kinetics, where reaction rates and mechanisms can be studied using spectroscopy while a reaction takes place. Now, let's discuss the applications of spectroscopy. Spectra can be used to detect and identify and quantify the information about the atoms and molecules in various fields from astronomy to biochemistry. In astronomy, the spectroscopy can be used to analyze the spectra radiation emitted by distant stars, galaxies, and planets. This can be used to find the chemical composition, physical properties like temperature, density, etc. of distant astronomical objects. In environmental science, the remote sensing, pollution, soil composition, vegetation, etc. can be obtained using satellite imaging, and this also works based on spectroscopy. In material science, characterization and quality control of metals, polymers, etc. can be done using spectroscopy. Chemical kinetics is one of the important areas where spectroscopy gives us insights into kinetics and chemical reactions and the presence of intermediate radicals, unstable species, which emit radiation during the reaction. In biochemistry, the protein structure, DNA analysis, and diagnostic tools use spectroscopy. In all these applications, identifying unknown substances and quantifying elements and compounds is a key application for spectroscopy. As we can see in the picture provided on the right side, the schematic shows that the light that directly comes from a hot source, which is like a star, when it reaches Earth and the spectrum of that light is captured, then it probably shows continuous spectrum. However, when the light from the hot star it passes through a gas nebula, which is a dense cloud of gas, then this gas absorbs energy from this light as the light passes through it. After this energy is absorbed by the gas, if the light transmits through this gas cloud and that transmitted beam is captured and spectrum of that is obtained, then it shows a continuous spectrum with black lines on it. These black lines corresponds to the specific wavelengths corresponding to the energies which the gas has absorbed. On the other hand, once the gas molecules absorb this energy from the incident light, the molecules or atoms get excited, and when they come back to ground state, they emit that energy as radiation as well. And when this emission is captured and the spectrum is obtained, this looks like something that we have already discussed, in which bright lines are present on dark background. So, when bright lines are present on dark background, then it's called emission spectrum because it is emitted by the gas molecules after the molecules de-excite to ground state. Whereas the spectrum that is obtained directly from the transmitted light from the star which has passed through this gas nebula, it is called absorption spectrum because dark bands corresponding to the energy absorption by the gas nebula are present in this spectrum. Now, let's discuss the two types of spectrum that we have seen, absorption spectrum and emission spectrum. In emission spectrum, as we have discussed before, the molecules in a hot gas, when they return to lower energy state, they emit radiation. And this radiation, when passed through a slit and converted to a beam, then pass through a prism, then the different wavelengths present gets deflected due, as we have already explained, the longer wavelengths deflect at shallower angles, whereas the shorter wavelengths deflect at steeper angles. This produces a line spectrum where different wavelengths present in the incident light emitted by the hot gas form different individual discrete lines on the spectrum. Since only these specific wavelengths are present in the incident light, the rest of the spectrum appears dark. Now coming to absorption spectrum. In absorption spectrum, when a high density hot matter such as a star, when it emits a radiation, that radiation contains all the spectrum, all the wavelengths. However, when that emitted light is allowed to pass through a gas cloud, then the molecules in the gas cloud absorb some energy from that light. And when we allow the transmitted light after the energy has been absorbed to pass through the prism, we obtain a absorption spectrum. In absorption spectrum, we see a continuous spectrum of different wavelengths which are originally present in the emitted light by the star. However, dark lines are seen in the spectrum corresponding to the individual wavelengths that pertain to the individual energy transitions that occur when the energy from the incident light has been absorbed by the molecules in the gas cloud. The different emission and absorption spectra for different elements has been shown on the right side, where we can see in the absorption spectra, dark lines or bands are present on a continuous spectrum, whereas in emission spectra, bright lines or bands are present on dark background. We can clearly see here that for all the cases, the absorption and emission spectrum complement each other. That means the summation of absorption and emission spectrum should give us continuous spectrum. Thus, to summarize, the initial energy radiation that is directly coming from the star, which is incident on the gas cloud, initially has continuous spectrum. However, when this radiation passes through the gas cloud, the energy is absorbed by the molecules inside the gas cloud, leading to the excitation of those molecules. Subsequently, the gas cloud molecules return to ground state and emit radiation having discrete bright lines on the dark spectrum. This is nothing but the emission spectrum corresponding to the molecules in the gas cloud. On the other hand, the spectrum of the initial radiation after the energy has been absorbed by the gas cloud, that is, spectrum of the transmitted light radiation, is absorption spectrum, that is, dark discontinuities on continuous spectrum. Thus, the emission and absorption spectrum complement each other because the same energy levels and transitions are involved in both the cases. Hence, the emission and absorption spectrum together form a continuous spectrum, and this is taken advantage of in the fields like astronomy by indirectly estimating the composition of planets using absorption bands compared to the continuous spectrum of the light from the respective star. It is interesting to note that even the solar spectrum that we receive from the sun shows dark absorption bands which provide information about the chemical composition and temperature of the sun itself. Here we can see the image on the right side where this is a solar spectrum. Even though the light coming from the star originally has continuous spectrum, as the light passes through the hot gases and exits the sun atmosphere, those gases in the sun's atmosphere absorb different energies from that radiation, thus forming these discrete dark patches or discrete dark lines in the solar spectrum. Thus, the spectrum that we receive from the sun is effectively absorption spectrum. If that corresponding photon is originated at the core of the sun and has to travel through different layers of the sun before reaching Earth. Thus, the dark lines or patches present in the solar spectrum can be used to estimate the composition of different layers of the sun and other properties such as temperature, density, etc. Now, let's discuss Beer-Lambert's law. The absorption of the energy in an incident radiation as it passes through a medium can be understood using Beer-Lambert's law. It is a fundamental principle in spectroscopy that relates the attenuation of light to the properties of the material through which the light is traveling. Mathematically, the Beer-Lambert's law is expressed as the light intensity of a monochromatic light radiation exponentially decreases with the travel distance through the medium and the concentration of the absorbing substance as it passes through the transparent medium. So the relation is shown here in mathematical terms as A, which is the absorbance, that is log of the ratio of the initial radiation intensity and the radiation intensity after passing through the medium. Thus, absorbance is equal to epsilon Cl, where epsilon is the molar absorption coefficient, C is the concentration of the sample, and L is the travel distance through the medium, which is width of this medium. Here, the transmittance is I by I naught, which is the ratio of the transmitted radiation intensity to the incident radiation intensity. The transmittance of a radiation through a medium can be used to estimate the concentration of a compound with known absorption coefficient in a transparent mixture. Now let's see one of the applications of emission spectroscopy, which is combustion studies. Emission spectroscopy is a powerful tool for studying combustion processes. By analyzing the light emitted from a flame, researchers can gain valuable insights into the chemical composition, temperature, and reaction kinetics of combustion processes. The different ways in which emission spectroscopy is used is identification of reactive species, which are radicals and intermediate species which occur during the reaction pathways in combustion. Also, the intensity of the spectral lines emitted by these species from the flame is directly related to the concentration of the emitting atoms. Next, this also helps in determining the combustion efficiency by studying the presence of different product species using emission spectrum of the product gases. Next, emission spectroscopy can also be used to monitor the formation of nitrogen oxides, NOx emissions, soot, and other pollutants. The study of flame structure and flame dynamics and visualization will give us the information about the distribution of species, the flame front location, and flame heat release dynamics, which will help us in optimizing the combustors. Now, let's see the different experimental techniques that are used in combustion studies, which are based on spectroscopy. The first one is optical emission spectroscopy. In this one, the species which has to be studied is introduced into a flame, and the light emitted by the species after getting excited using the flame is measured. The other kind of technique is LIF, laser induced fluorescence. Here, laser is used to excite specific species inside the flame and their fluorescence is measured. Extension of this technique, which is planar laser induced fluorescence, is a technique that provides 2D images of species distributed within a flame. For this, a laser sheet is used, which is created using sheet making optics. Another technique which is important in combustion studies is chemiluminescence. As explained before, chemiluminescence occurs when the light is emitted by a substance due to the energy generated during chemical reaction. In combustion studies specifically, during combustion, due to chemical reaction which is exothermic in nature, that energy is used by the intermediate species which get excited to higher energy states, and when they de-excite to lower energy states, they emit radiation at specific wavelengths. The measure of this intensity of light emitted by these excited species formed during chemical reaction during combustion is chemiluminescence. By employing such techniques, the researchers can gain deeper understanding of combustion processes, optimize engine performance, and develop clean and more efficient combustion technologies. Using these visualization techniques, we can obtain spatial resolution, that is, visualization of the spatial distribution of different species within the flame, and temporal resolution, which is time-resolved spectroscopy that can capture the rapid changes in the flame structure and chemistry. So, the chemiluminescence spectroscopy is similar to atomic spectroscopy, which uses quantitative measurements of optical emission from excited chemical species to determine concentration. The primary difference is that it measures emissions from energized molecules during chemical reaction instead of simply excited atoms. The spectra obtained by this technique emanate from molecular emissions, which are broader and complex bands. The chemiluminescence can take place either in solution or gas phase, whereas the atomic emission spectroscopy is almost strictly a gas phase phenomenon. The chemiluminescence, by its name, suggests that the light is generated from chemical energy and does not come out from external lamp. Thus, the problem of scattering of the radiation from the excitation source is completely avoided, as there is no external lamp or laser used in chemiluminescence. Next, let's see specifically how chemiluminescence occurs in terms of chemical reaction. in chemiluminescence, the generation of light, is due to chemical reaction as explained before. Here, as we can see, reactants A and B combine, they form products and they produce light. For achieving chemiluminescence, the exothermic reaction has to generate sufficient energy to excite electrons from ground state to excited state. This is important criteria. So, in general, exothermic oxidation reactions are capable of chemiluminescence. So, to be precise, the following reaction shows the intermediate radical C star which is formed in the products, that is in electronically excited state, which may subsequently relax to ground state by emitting a photon. So, when the reactants A and B combine, they form an intermediate species C star which is unstable and in excited state. Now this C star radical de-excites to ground state emitting light. This is what happens during chemiluminescence in combustion reactions. So as explained before, depending on the energy difference between the excited state and ground state of this specific species, the energy of the photon is dependent, which determines the wavelength at which the light emission occurs. Thus, by isolating and allowing only a specific wavelength into the camera by using a specific bandpass filter at that specific wavelength, we can measure chemiluminescence at that specific wavelength and obtain spatial distribution of that specific species inside the flame.